Okay, so first looking at just a differential equation. A differential equation is an equation that contains an unknown function and some of its derivatives. So actually we just saw one of these above. Okay, if I take a look here at dy dx equal to 2x minus 1, okay, we have this is a differential equation. We also saw one back in Cal 1, okay, when you're thinking of simple harmonic motion. Okay, simple harmonic motion was defined in terms of a differential equation. In fact, it was a second order differential equation, which meant it included the second derivative of our function. So for differential equations, it said that the second derivative of displacement was a constant multiple of displacement itself, and in fact that constant was negative omega squared. So that was our differential equation for simple harmonic motion. You could also, let's throw in a third one here. Let's say y double prime. So we have our second derivative, and we have minus 3y prime. So we have also our first derivative, and maybe that's equal to minus 2 times y. So here we have three differential equations, and we're going to be looking specifically at separable ones. Okay, and specifically at first order equations, so they're not going to involve anything like this where we have the second derivative, but in general this is what a differential equation could look like. Okay, now that we know what differential equations look like, let's take a look at what our solutions look like to these differential equations. So specifically, let's take a look at this last one. Y double prime minus 3y prime is equal to minus 2y, and let's do an example here to show what these solutions look like. Okay, so let's take a look at this. Here we're going to show that this function, y equal to a e to the 2x plus b e to the x, is a solution to this differential equation that we just saw. So what does it mean to be a solution to a differential equation? Well, similar to our other understanding of solutions, it simply means that if I plug in here our function y, and I plug in here y prime and here y double prime, I should end up with equality in this equation. Okay, now in order to do that, we have to figure out what is y prime and what is y double prime. So first, what is y prime? So we're going to have to do a little bit of a chain rule here. We get 2 multiplied by a e to the 2x. And for, let's clean that up a bit, plus b times e to the x. We can now also find y double prime. Y double prime will be 4 multiplied by a e to the 2x. Plus still b e to the x. That function is its own derivative. So now we have y prime, we have y double prime. Go back to our differential equation, we can sub everything in. So on the left hand side, we can replace y double prime. We get 4 a e to the 2x plus b e to the x. That's y double prime minus 3 times y prime. And y prime we know is 2a e to the 2x plus b e to the x. Okay, so this right here, let's set this up a little bit nicer. Whoops. Gotta love that. A little bit of technical difficulties. Okay, let's bring that over to the side. So this is the left-hand side of our equation. And we want to show it's equal to negative 2y, which is the right-hand side of our equation. So we can simplify. And really, let's just sort of expand that right-hand side. So we get minus 6 times a e to the 2x minus 3b e to the x. And now collecting similar terms here, we end up 4a minus 6a, we get negative 2a e to the 2x. And we have b e to the x minus 3b e to the x is going to be minus 2b e to the x. And now all we want to do is show that this is equal to minus 2 times our original function y, where y was a e to the 2x plus b e to the x. So all we have to do is factor this, minus 2 from both terms, and we should be done. So here we get minus 2 times a e to the 2x plus b e to the x, which of course is equal to minus 2 times y. And so indeed, we end up with this function is a solution to this differential equation. When we plug in our function, our first and our second derivative, we end up with equality. Okay, so that's what it means to have a solution to a differential equation. That's going to be a big part of what we look at with separable differential equations, is how to find these solutions. Okay, so now just a couple more definitions, and then we'll look at how to solve separable differential equations. Okay, so now that we know what a differential equation is, let's take a look at a separable differential equation. So it's specifically just a differential equation in which your derivative can be factored, and you can literally separate it as a function of x multiplied by a function of y. So it's going to look something very much like this. And then what we're going to look at now is how do you go about solving this. Okay, if you have separated your differential equation in this way, you have dy dx written as a product of a function of x and a function of y. What do we do now? And the steps are going to sort of always be the same from this point on. What you're going to do is further separate it. Let's rewrite this so we don't mess up our definition. But here, if I have dy dx, in general, I have written it as a product of a function of x multiplied by a function of y. What do we do to solve this? So the first thing is we just further separate it. I'm going to take this differential for x, I'm going to bring it over to the right-hand side, put it together with this function of x, and then we're also going to take here this function of y, we're going to bring it over to the left to put it with the differential for y. So we do these two things. Okay, and afterwards it's going to look a little bit weird written like this, but in general the examples will be a little bit easier. So to bring over the f of y, we actually need to divide by f of y. So on the left we have dy divided by f of y. On the right we have g of x multiplied by dx. And now that we have further separated x from y, at this stage all you're going to do is integrate both sides. Okay, so that's sort of really the last step here. We integrate both sides. And then you'll be putting in your plus c, and ideally solving for y as a function of x. Okay, but that's enough sort of dealing with this formal definition. Let's actually do an example together. Okay, so we're going to start off with this one. Again, it's not overly difficult, but mostly I want to show you how we're going to be dealing with that constant c. So here we're going to solve this differential equation. You can see already it's sort of being separated for us. We have dy dx on the left, and on the right hand side we have our function of y, which would be 1 over y squared, and then we also have our function of x, which would be x squared. So we don't specifically need to write it like this, okay? Normally this would be sufficient, but you want to realize that here we have managed to separate it as a function of x times a function of y. So now, like we said before, we're going to bring over to the left-hand side all of our y variables, and we're going to bring over from the left-hand side our differential for x. And that's going to leave us with dy multiplied by y squared equal to x squared multiplied by dx. And then what do we do at this point? We are now going to integrate both sides. And if we integrate both sides, we have 1 over 3 y to the power of 3. On the left, we don't need to put in our plus c here. That's what we talked about earlier. We only need to put in the plus c on one of the two sides. On the right hand side, we have 1 over 3 x to the power of 3, and this is where we'll put in our plus c. Okay, so here we're done integrating, okay, and if you wanted to, you could leave here y implicitly defined as a function of x, but in this case, it's really not much more work. We're going to solve for y, and really that just requires us to do a couple things. So the first thing is we're going to multiply both sides here by 3, and this is where you have to realize that yes, we're comfortable doing this with the x and the y term, but usually when we're dealing with antiderivatives and general antiderivatives, we just leave this plus c alone. However, this constant now has to represent the same constant going from this line of the equation down to this line. So I cannot leave it as just c. If I'm going to multiply both sides of my equation by 3, I need to also multiply this constant by 3, and so our equation becomes y to the 3 is equal to x to the 3 plus 3 times c. Messing up this constant is one of the most common mistakes that I see with differential equations. Okay, so make sure you treat it as a constant. Whatever you do to one side, you must do to the other side. So now the last thing is to finish solving for y, we're going to take the third root here of both sides. We get y is equal to the third root of x to the power of 3. And this 3 to the c, that's going to need to be inside the square root, not outside the square root, because we are doing the cubed root to the entire right-hand side. And so this, right here, this is actually y solved for as a function of x, and this is what we would now call our general solution. And that's our general solution to this differential equation. Let's take a look at one more definition, and then we'll come back and sort of take another look at this example. Okay, so we saw this before actually in the first question that we did. If you're looking at the problem of finding a solution to the differential equation satisfying this condition, y of t0 is equal to y0, this is called an initial value problem. Now, this way of representing it I find actually a little bit unnecessarily complicated. This is the same as what we saw before. An initial value is really just a point on your curve. And in this case, the point on our curve says that if t is equal to t naught, then y is equal to y naught. And that's the point that our curve has to pass through. So now let's go back to that previous example, and we're going to turn it into an initial value problem. And really, you'll see all we're going to end up doing is solving for that constant c.